AP 120, Chapter 17, Topics, Nephron and Glomerular Filtration. So, as I mentioned in the previous part of this chapter's lecture, the nephron, this interesting tubular structure, is the functional unit of the kidney. There are millions of nephrons in each kidney, and they are what is maintaining the proper composition of the blood. And they lie both in the cortex of the kidney as well as in the medulla. So the nephron is composed of two main functional regions. You have this spherical shaped structure called the renal corpuscle, where you'll find the glomerulus, and then you have the long tubular portion called the renal tubule. The renal corpuscle, its job is filtering out the some of the fluid from the bloodstream in order to allow for a proper adjustment of the blood's composition. So within the renal corpuscle, we have the glomerulus, which is a capillary bed. That fluid is leaving this capillary bed and is now called the filtrate as it enters the nephron officially. And then, of course, we have the glomerular capsule, the structure surrounding the glomerulus that has a capsular space that will fill with that filtrate and then allow it to move on to the rest of the nephron. So from there we get to the renal tubule, which is broken up into a few parts. Directly after the renal corpuscle is the proximal convoluted tubule. Proximal because it receives the filtrate immediately, coming directly after the renal corpuscle. Convoluted because it's twisted up, and tubule because it is tube-like. That then will carry the filtrate into the medulla, into the nephron loop. Nephron loop having two portions, the descending limb carrying the filtrate down into the medulla, and the ascending limb carrying the filtrate out and up into the cortex again. And then it reaches the distal convoluted tubule. Distal because the filtrate is traveled farther from the renal corpuscle, convoluted because it's twisted up, and tubule because it is tube-like. From here, the filtrate will enter a structure called the collecting duct. The collecting duct will be collecting urine from many, many nephrons. So once the filtrate enters the collecting duct, it is no longer in a nephron, and it is officially considered to be urine. The urine is then carried down to the papilla, the renal papilla at the apex of the renal pyramid, and then it'll empty out into the minor calyx and then eventually make it to the urinary bladder. So, the flowing of fluids. Blood is arriving in the glomerulus. Being a capillary bed, the glomerulus allows fluid to leave and enter the glomerular capsule, where it is now filtrate. From here, the filtrate travels to the proximal convoluted tubule, the descending limb of the nephron loop, the ascending limb of the nephron loop, and then the distal convoluted tubule. All during that time, the filtrate's composition is adjusted, as well as the composition of the blood is being adjusted. And then the fluid enters the collecting duct, where it is now officially urine. Collecting duct going to the minor calyx, then the major calyx, then the renal pelvis. Then it exits the kidney, enters the ureter, goes to urinary bladder, where it is stored until eventually released via the urethra. All right, so here I've stretched, or the artist has stretched out the nephron to sort of separate where the different functions of the nephron are occurring. Here's the glomerulus, here's the, in theory, the peritubular capillaries are twisting around the nephron. So, to start off with, we have this structure adjacent to the nephron called the Juxtaglomular Apparatus. It is composed of the ascending limb of the nephron loop and the afferent arteriole in which blood is arriving to go into the glomerulus. And the importance of the juxtaglomular apparatus is it regulates the blood pressure in the glomerulus, in this capillary bed, and also it decides whether or not to secrete the hormone renin. This is important. We want to control the blood flow into the glomerulus. because we want the blood pressure to be high enough so that there is plenty of filtrate being produced and released into the glomerular capsule, but at the same time not too high, because if the blood pressure is too high, the glomerulus could become damaged. And the way it controls that is by the constricting or dilating of the afferent arteriole. If it dilates, more blood enters the glomerulus, increasing the blood pressure. If it is constricted, less blood enters the glomerulus, lowering the blood pressure. So we have the glomerular filtration occurring in the glomerular capsule. So again, fluids are leaving the glomerulus and entering the glomerulus capsular space. There is a lot of fluid in exiting the bloodstream. We end up producing about 180 liters of fluid per day. That's an awful lot. Luckily, we have other processes that return most of that to the bloodstream. And those include the tubular reabsorption and tubular secretions. So after filtrate is produced in the glomerular capsule, it enters the renal tubules, where there's tubular reabsorption. Most of the fluid is returned to the bloodstream. We do not want to be urinating 180 liters a day. And then there is some tubular secretion to fine-tune the composition of the blood by returning some things like electrolytes to the filtrate. So tubular reabsorption going back into the bloodstream, tubular secretion going from the bloodstream back into the nephron. So when we look at the filtration structure, we see that we have, of course, the capillary, the glomerulus, that has fenestrations, little openings to allow fluids to easily leave the bloodstream. And then we also have on top of the glomerulus the podocytes. Podocytes are cells, part of the glomerular capsule. They're the inner layer of the glomerular capsule, lying directly on the capillaries, lying directly on the glomerulus. And this helps to limit the size of things that can leave the bloodstream. So the only things in the filtrate is water, electrolytes, glucose, urea, uric acid, other small things that can leave the bloodstream. Anything, though, the size of a protein or bigger cannot leave. So we're filtering out, we're preventing things protein size or bigger from leaving the bloodstream. So that, again, is very important. We do not want proteins and cells to leave the bloodstream and enter the nephron. Only smaller things dissolved in the water. So if we look at the composition of blood plasma in terms of small things like electrolytes and other substances like glucose and urea and uric acid, we see that the composition of plasma and composition of the glomerular filtrate are basically the same, which makes sense. We're just moving fluids from the plasma into the glomerular capsule. But obviously, the filtrate in the glomerular capsule won't have the bigger things like plasma proteins. The fluids are leaving the capillaries because of the high hydrostatic pressure, aka the high blood pressure in the glomerulus, and it's high enough that things are always leaving. The net pressure is moving fluids out of the glomerulus. Nothing is returning back to the bloodstream, which is uncommon. Usually with capillaries, fluids and materials leave, and then fluids and materials return. But in the glomerulus, in the nephron, fluids only leave the entire time. The fluids with the various electrolytes and other substances dissolved in it are leaving, not returning. And of course, that means that the blood pressure in the glomerulus is the highest blood pressure for capillaries. Pretty low compared to blood pressure in general, but for capillaries, it is very high, which is why we need to be very careful in maintaining that high blood pressure so it doesn't get too high. Also, the reason why the blood pressure is so high is because the efferent arteriole is much smaller in diameter than the afferent arteriole, so more fluid is entering than exiting, helping to drive the release of fluids out of the capillaries. So again, glomerular hydrostatic pressure is the dominant force countering other pressures trying to return fluids back to the bloodstream. Again, we can regulate this blood pressure by having the afferent arteriole constricting. If it constricts, then less fluid, less blood is entering the glomerulus, lowering the blood pressure in the glomerulus, which means less filtrate is being produced. And then the efferent arteriole can be constricted. When it's constricted, that would increase the pressure in the glomerulus because less fluid is exiting, less blood is exiting, so more filtrate is leaving. All right, so filtration is about 180 liters a day. Most of that fluid gets reabsorbed by the renal tubule, which is awesome because if reabsorption didn't occur, then we'd have to urinate 100 times more often than we currently do, and that would suck. Again, what is controlling these processes of regulating the amount of filtrate leaving includes the glomerular juxtaglomular apparatus. The juxtaglomular apparatus is controlling the blood pressure of the glomerulus, controlling the production of filtrate. And there are various things that help to regulate the activity of the juxtaglomular apparatus. This includes blood pressure, overall blood pressure in the body. If that should drop, then that would mean that less filtrate can be produced. So the juxtaglomular apparatus would try to compensate for that. We also have stimulation directly from the brain. And then there is the juxtaglomular apparatus observing the concentrations of electrolytes in the filtrate in the ascending limb of the nephron loop. So it has receptors detecting the composition of these electrolytes. And if these ion concentrations get too low, then the juxtaglomular apparatus will want to increase filtration. So the juxtaglomular apparatus and the efferent arteriole, they are able to stimulate the secretion of renin, which then leads to a whole complicated hormone chain of events that eventually lead to the production of angiotensin II that will cause the efferent arteriole to constrict. This then acts as a bottleneck, preventing fluid from as efficiently leaving the glomerulus, causing more filtrate to be produced. So it counters a decrease in blood pressure to keep the pressure in the glomerulus high enough to allow for efficient production of filtrate. So angiotensin II also stimulates the secretion of aldosterone, which is another hormone that's important. And this stimulates the reabsorption of sodium and water, so that the renal tubule is going to increase the amount of water and sodium that is being returned to the bloodstream. By doing this, this will conserve water, which is trying to keep the overall fluid levels in the blood higher, so overall blood volume higher. That will hopefully keep the blood pressure as high as possible. And as a consequence, aldosterone leads to more concentrated urine being produced. So basically, we have in the bloodstream this precursor, angiotensinogen. You don't remember that name, but it's always in the bloodstream. When the kidneys are detecting low blood pressure, low blood volume, it will release the hormone renin, which leads to angiotensinogen becoming angiotensin II, which is what we consider the important hormone. That then does a variety of things, vasoconstriction of the efferent arteriole, which is increasing the blood pressure in the body in general, but also in the kidneys so that we have proper filtration. Also the secretion of aldosterone and ADH, and these hormones are going to lead to more concentrated urine, which will lead to more water and sodium being reabsorbed by the nephrons. And also, angiotensin II causes us to feel thirsty, which means we will hopefully drink more fluids, which will increase the overall blood volume. The goal here being to get blood pressure up, both in the kidneys, so that we're getting proper filtration and monitoring of the blood composition. And I want to finish